Let's use this shallow water model to do some experiments with heating imposed on the equatorial band and at 30 north for representing a monsoonal heating. So that's our mass source, which acts as a convection related pumping into the upper atmosphere with the structure we saw before, where A is the heating or the forcing, and the solution for the equatorial or maritime continent heating looks this way. It has some observed realistic features, but of course there are differences from observations because this is a very simple model with a simple heating. Nonetheless, you clearly see the potential vorticity up here that is crossing into the westerly duct that exists here. Much different than the real observations, of course, but the flux across 30 north shows a little southward transport compensated by the northward transport, and at 10 north it's a little bit more wavy, more crossings because the heating is in the tropics closer to 10 north, but basically agrees with the ideas we have already seen from observations and the arguments we made about why you cannot have just northward previous advection. You need compensating southward advection somewhere in the latitudinal band to maintain the global balance of PVS transport across latitude. Okay, the monsoonal experiment with the heating imposed at 30 north produced much more strong and clear response of the PVS advection into the westerly duct, eastward advection and back. So you can see the PV trough clearly as we saw on the 370K in July, corresponding to the monsoon heating and circulation. This is the PVS flux across 30 north, much larger southward flux compensated by smaller global northward flux, and at 10 north again you have a strong southward flux and northward flux compensated across the rest of the latitude. So even with this simple shallow water model with imposed heating or mass source equivalent in this case, you get the solution that the PVS is conserved on the isentropic surface in the upper level. You can look at the transients associated with this. So these are snapshots of PVS after the heating is imposed for the monsoon experiment at time unit 1, 3, 5, and 7. And here you get a much better sense of the breaking of the PVS into filaments and so on. So you can see here it's clearly breaking off and getting mixed around and dissipated. As we argued before, that PVS dissipation in the deep tropics is contributing to maintaining the mean zonal upper level circulation. Okay, so diabatic heating in the low latitudes is providing the PVS, the westerly jet, the southward invasion at the outlet exit region through the westerly duct, and then the dissipation of the PVS that is transported southward into the deep tropics is breaking, dissipating, and adding to the mean zonal circulation. So these are interactions at multiple scales that we will look at later on. Okay, maybe I should leave this for the next podcast. This is a short one, but just get used to the idea that even with the shallow water model, we can derive this upper level circulation and the tropical, extratropical synergy, if you will, in terms of how the diabatic heating in the tropics is pumping eddy fluxes into the extratropics, and how extratropics is pumping PVS back into the tropics, and that is helping maintain the zonal circulation. Okay.